With a solution in hand for the electric field, now let's derive the magnetic field for this plane wave from the electric field. Okay, so what about that H field? We made the simplification for the electric field, the total electric field on our plane, our XY plane where we have this uniform plane wave. We made the assumption that the electric field would just be pointed in X. So what would happen to H? Would it have X component and Y component, just one component? Would it be more complex? Let's see what happens, and we can figure this out from the Faraday equation. And already from this, we should, just seeing this curl, this should start giving us the idea that the relationship is going to be a perpendicular relationship. So we can take that right-hand side where we have the field H, and we can break that out into its components where we have X, Y, Z component. Now, on the left-hand side, right, this curl equation, right, this is going to give us this. So we should be able to do something now where we work towards equating the X direction of the right-hand side with this curl part. So let's keep going with this. All right, so the curl of E gives us this, and when we look at this, we already know that we made the simplification that the Y direction would be 0, right? This was a simplification we made. And then previously, what we saw was that the Z direction must be 0. So for a wave propagating in the Z direction, we actually don't have a field component that's pointed in that direction. A little strange, but that's how it is. That's what came out of the math. All right, and then we made a further assumption that the forward traveling wave, so this plus part, right, this is the one that mattered, and we won't concern ourselves with the reverse traveling wave, which doesn't have as much physical meaning for a plane wave that's kind of propagating out through infinite space, never reflecting back. So we simplify our e to the x component down to this. Now, we might call this, for simplicity, we'll just call this entire thing e to the x is a function of z. We leave that plus part to denote that it's the forward traveling wave, and then still we have the phasor component to denote that this is the magnitude of the phasor, and it's in the x direction. All right, so on the right hand side we have the magnetic field broken up into those XYZ components, and then we took this curl and we made our simplifications where we know that the y and z parts are 0. Now let's actually do perform the curl. We get all these partial derivatives, and we can see a lot of this is going to go to 0, right? So all of these terms are actually going to go to 0. Now that leaves us with two terms that we need to concern ourselves with, which have this e to the x in it, which we know is actually the forward solution to that electric field. And so simplifying it down now, we can see that the magnetic field is in the x direction. It's definitely going to be 0, right? So it's not going to have any x component. So h of x must be 0. But we have these two partial derivatives. And now let's think about if any of these are actually going to go to 0. And in fact, the partial derivative with respect to y will go to 0. And right, we know that this is only a function of x, so it's constant with respect to y. And so for that reason, right, this term will go to 0. And now we can start to be able to see that by equating these vector magnitudes, hx is 0, hy is going to actually have a value, and the z is going to be equal to 0. Okay, so now we simplify to this, and gives us these components, and we are starting to get quite close to seeing what the hy is going to be, what the hy is going to be. So from here, let's do some rearranging. Let's get this over to this side. Let's take that partial derivative. Okay, so when we move that over, take the partial derivative, we plug in our knowledge of that equation, our forward traveling solution. We take that partial derivative, this minus jk comes out, and then we still have this minus 1 over minus j omega mu. Now let's see, some of that should cancel, some of those j's cancel. We're left now with the h, right? So this h component, this in the y direction, and we have on the right hand side, we can see that the magnetic field is written in terms of the electric field. Okay, so that's kind of convenient because we already have discussed this coefficient to the electric field. Now, what about this leading part? Well, we will define this whole thing as hy0 plus, and we can say that the hy0 plus is actually kind of a function of that electric field coefficient. All right, now this gives us, for the full phasor, if we go back from the scalar form, right? So this is the scalar, the magnitude in the y direction. If we go back now to our full phasor, which does have those vector components, we can see that we just derived this magnitude, and therefore we can write the complete magnetic field is going to be in the y direction, which is in fact perpendicular to the electric field, has this coefficient, which is a function of the electric field coefficient. And from here, we can see that there's a lot of parallels, right? We know that this coefficient is actually contained inside of here, and we can see that these are going to be perpendicular to each other. So if we selected that the electric field was only in the x direction, based on the Faraday equation and that curl relationship, the magnetic field is only going to be in the y direction. Okay, so that will look like this on our plane. These are 90 degrees separated from each other. We know that the propagation is in the normal direction for this. This is what we derived for the electric field. The normal is in the z direction. And so we call this case the transverse electromagnetic wave. And it's transverse because of these properties where the electric field and the magnetic field are 90 degrees related to each other from in the plane, and then the direction of propagation is also 90 degrees normal to that plane that those two create. So these solutions are for the transverse electromagnetic, or TEM, wave. And these are some other kind of 3D comparisons of what this should actually look like. And here's a bit of a video. Hopefully this helps you also understand or see why we say that the wave is propagating in the z direction, but the electric and magnetic field maintain this perpendicularity to each other. And then all throughout here, right, we can see that everywhere on this plane, so if we just checked some random xy plane like this, we can see on this that the plane wave is uniform in this case, and that was what we just spent our time deriving, the plane wave in this uniform case. All right, so thank you, and I'll see you in the next video.